Right. Hi, grade XC. Here we are back online, and I haven't even got to see you. I'm sorry. I was really looking forward to it. But now we're going to start a new subsection within the cell structure. And this is a section where we're going to talk about line scales, or scale lines, or scale bars. And hopefully on many of the electron micrographs that we've looked at so far, you will have noticed these little scale lines or line scales. And what this means is, and it's exactly the same as the geography ones that you have on a map. You know how in geography you've got a linear scale, and it shows you how much map distance represents in real, actual, on-the-ground distance if you had to travel it. So in other words, if you use the scale line and it says to you, this distance on the map represents 5 kilometers from point A to point B, represents 5 kilometers because it's that far apart, and you get into your car and you drive the distance from point A to point B, then it's going to be 5 kilometers. Okay, so the kind of line scale that we use in life sciences is exactly the same as a geography line scale. What it's saying to you is this distance on the cell, anywhere on the cell, represents 2 micrometers in reality. This distance on the cell, on the image, equals that distance in actual reality. And what this line scale can be used to do is to measure how big, how long, how wide, how whatever anything is on this micrograph. So I can say to you, use the line scale to tell me how long this chloroplast is from this bottom part all the way to there in real life. And then you'd use the line scale, and I'm going to show you how to do it. You're going to do it as a ratio. And this is one of my favorite calculations. It just makes so much sense. So here, for example, there's a little line scale here, and it says this distance from there to there, anywhere on this image, represents 5 micrometers. So the figure on the scale, oh, that's his sail, actually means scale, represents the real actual distance. So this figure is the real actual distance, and this is the distance on the image. Okay. So we're going to do it, as I said, we're going to use this like a ratio. And ratios are awesome because the golden rule with ratios is what you do to one side, you do to the other side. So let's pretend that lockdown is over and you're going on a hike with 7 of your friends. And your friends discuss what to take with to eat for energy when walking. And it's decided to get packets of trail mix. So you volunteer to go to the shop to buy them. When you get to the shop, you find that the trail mix is advertised at 100 Rand for 12 packets of trail mix. But you only need 8 packets. How much will you pay for 8 packets? So to work it out, as I said, you're going to work it as a ratio. So you're going to say 12 packets equals or represents 100 Rand. And another nifty thing about ratios is that you can have totally different units of measurement on both sides of the ratio, because here it's packets of trail mix and there it's rands. you've got to now convert and will calculate how much one packet is. Don't skip this step out because then you'll lose marks. So if 12 packets costs 100 Rand, one packet costs, and now what have you done to this side? To get this side to 1, you divided it by 12. What's the golden rule of the ratio? What you do to this side, you've got to do to that side. Let's see how. I need a lot more sleep than I'm getting at the moment. Okay, so one packet is 100 Rand divided by 12. Therefore, 8 packets, and what have you done to this side? You've multiplied it by 8. So what have you got to do to that side? Multiply it by 8. So 100 Rand divided by 12 multiplied by 8 equals 66 Rand 66 cents. Okay, so again, it's a ratio. 12 packets costs 100 Rand. One packet, what did you do here? You divide it by 12. What do you do on this side? You've got to do on that side. So one packet represents 100 Rand divided by 12. Therefore, 8 packets, so you've multiplied this side by 8, equals 100 Rand multiplied by 8 divided by 12 equals 66.6 Rand. Does this look feasible? It does. Because 8 packets is almost, no, I'm going to get myself into trouble here. A third, almost a third. Yes, it must be a third-ish. Okay. And therefore, 66 Rand is about a third of 100 Rand. And so, yeah, great. Now, don't write this stuff here. I wrote it there to just help you know what we're doing. Okay, so there are also lots of line scales in life sciences, and you're going to work with them like a ratio. They serve exactly the same purpose as a line scale on a map. So here we've got a little sperm cell, or a part of a sperm cell, and here's a line scale, and it says that length equals 5 micrometers in reality. Now remember, I'm working on a laptop here and recording this lesson, so I'm going to measure it on my screen. So the line of the scale represents the measured distance or length. If I measure it on my screen, it's 2 centimeters. So if I put a ruler here and measure this, it's 2 centimeters. Okay. So the figure written on the scale represents the actual distance or length. Therefore, 2 centimeters on the image represents 5 micrometers on the real object. So in order to calculate the actual length of the head of the sperm, you do this. You write, but you don't write on my screen because it's on my screen, it's not going to be on your screen. Scale line is 2 centimeters. The length of the head on my screen measures, so I took a ruler and I measured from that point to that point, and it was 2.2 centimeters. So 2 centimeters represents 5 micrometers. Therefore, 1 centimeter represents 5 micrometers divided by 2. And, don't you dare write and, 2.2 centimeters. So I've multiplied this side now by 2.2. Let's multiply that side by 2.2. Represents 5 micrometers multiplied by 2. Okay, let's talk about the 2 points just now. Divided by 2. So the real or actual length of the head of the sperm is 5,5 micrometers. Okay, don't write this whole story. Life is too short to write this whole story. Just write 5,5 micrometers and I'll know what you mean. Now, I'm terribly sorry, but I come from a generation way back in the day where we never used to say 2,2. We used to say 2.2. So very often you'll hear me say a point when I actually am referring to a comma, but I'm old and I can't learn new tricks. Also, most times I prefer it if you work in millimeters. It's just so much easier to you remember all your conversions of millimeters, put them on this thing. Please let me have put it on this thing. No, I didn't. So remember, we long ago discussed that 1 millimeter equals 1,000 micrometers, which is this thing. And this is how you write micrometers. 1 millimeter equals 1,000 micrometers. And 1 micrometer equals 1,000 nanometers. So 1 millimeter equals 1,000,000. What have I just said? 1 millimeter equals 1,000,000 nanometers. Okay, are you right with that? Can you remember that? We did do it once upon a time when we were doing calculations. Okay, so here we've got a line scale, and it says that length from there to there represents 200 nanometers. So how long is this actual bacterium from where I put a line here and labeled it X and a line there and labeled it Y? So I've just drawn that line there to show you where you've got to measure from. And normally we'll do that in a test. We'll go from point A to point B. Okay, so the length of the scale line, I put a ruler here on my screen and I measured 11 millimeters. And the length of the bacterium on the drawing is 76 millimeters. So, start. 11 millimeters represents 200 nanometers, because that's what it says on the line scale. Therefore, 1 millimeter represents 200 nanometers divided by 11, because how did I get from 11 to 1? I divided by 11. What you do on this side of a ratio, you do on that side of a ratio. So 200 divided by 11. Then here I measured 76. So 76 millimeters. What have I done here? I've multiplied this by 76. So I must multiply that side. 200 nanometers multiplied by 76 divided by 11. And the answer is 1,381,8 nanometers. Okay, you happy? Okay. All right. So there's another example that you can work through. But in fact, what we're going to do, and I'm going to try and swap now from this to a different document that you should have printed off of Google Classroom. It's a 2-page worksheet on Google Classroom that you need to print so that you can do the examples on it. Okay, so if I lose you, I will come back. Stop that share, and now I need to share something else with you, and that something else is this Word document here. Got it. Okay. Right, let's do this thing. Share screen, and we're working with this Word document. Yay! Yay! No, apparently not. No, that's not that Word document from Lana. This Word document. Okay. What have I done? Okay. Okay. Yay, I think I've managed. Okay. So you need to print this off of Google Classroom. Otherwise, you can't do the examples that I'm giving you. So this just does what I explained to you just now. And here is a worked example for you. So here's a line scale, And there's a red blood cell. In fact, there are lots of red blood cells here. And when you work the example, this is what you do. Okay, so it says, you must write, measured length of scale line equals, and here when I measure it, after I printed it, 7 millimeters. And the measured width from there to there of the red blood cell A is 27 millimeters. So now the question is, how wide is this red blood cell in reality? If you actually got a red blood cell, how wide would it be? So 7 millimeters, which was this line, represents 2 micrometers, which is this figure above the scale line. Therefore, 1 millimeter. So what have I done on this side? I've divided by 1, by 7. Well, what must I do on this side? 2 micrometers divided by 7. Therefore, 27, which is what I measured from here to here, millimeters, represents 2 micrometers multiplied by 27 divided by 7. And so the red blood cell is 7.71 micrometers wide. And does that make sense? You need to have a look at it always and see if it makes sense. If this length represents 2, this is about 3 times that length. So it would be between 6 and 7-ish, we think. Have a look. Sure enough. Yay, my arithmetic is perfect. Okay, so what I need you to do for tomorrow's lesson, I need you to print the worksheet and do this one and this one, and we will check it tomorrow. Okay, and then tomorrow I will carry on with the rest of this section. Okay, all right. See you after midterm break.